Geeksforgeeks problem of the day is count smaller elements. I have solved the problem just a while ago using binary index tree. There are several other solutions for this particular problem. One is using binary search, another is using balanced binary search tree, and another is using alternative implementation of binary index tree where value compression is used and array based binary index tree is used. So let's first see the problem statement. So we are given n positive integer array and we are required to count the number of smaller elements on the right side of each array index. Actually, array index should be mentioned here instead of just array. So let's see the first example. So the number of smaller element on the right side of 12 is 6. The number of smaller element on right side of 1 is 1. Actually, this is the smaller element. Similarly, for 2 and 3, the count is 1 each. Similarly, for the 11 and 4, the count is 1 and 0 respectively. In the second example, the number of smaller element is 0 for all the indices because the given array is sorted in ascending order. So there are no smaller element on right side of any of the element. In this problem, we are required to implement construct lower array. Yeah, so this particular method, so it accepts integer array and the size of the array as input arguments, and we have to return integer array of same size, and each index corresponds to the result of each array index. So basically the number of smaller elements on right side of each of the array index. So my approach of the binary industry uses map of the integer to represent the to represent the result for each of the index. So alternative approach could be array based binary index tree, and for that we would need to apply uh, value compression. So basically it is just for mapping the number of, it is just for mapping the array values to be between 0 and n minus 1. So yeah, so if we would have just used binary industry array based binary industry instead of this, we could have just written this value. So bit of index plus equal to val. Yeah, otherwise it is similar to normal implementation. Okay, and similarly for get sum, we are we are going to just use sum plus equal to binary index tree dot get value, get all default at index, because for a particular index, if that index is not existing, then by default 0 should be returned. It is similar to the normal implementation where we would write sum plus equal to bit at index. Okay, so I will not be explaining the actual logic of the binary index tree because there are already several of the tutorial and explaining materials explaining the binary index tree data structure quite in detail. So some of the blog posts and articles that I like, where you can also take a look at if you are not comfortable with binary industry or sandwich tree. One is cpalgorithm.com, another is top order blog post for binary industry, another is Hacker Earth binary industry blog post, another is uh, Code Forces and Code Forces. There are several other YouTube videos also that explains binary industry in detail. So let me just go into my logic of how I'm converting the problem into binary industry problem. So normally, you would already know that in binary industry we generally do these kind of query and update operations. So basically, point update and a range query, a range sum query. So range sum query is like sum from the beginning of the array to a given index, and here we are doing the same. So instead of going from the forward direction, we will go from reverse direction. So whenever we are at a particular index, we will first query the sum of the element. Okay, so while updating it, we are always adding 1 to the particular value. So suppose we are at 4. So first we will query what is the result up to 3. Here, due to this part of the logic, so basically index can't be equal to 0, otherwise it will result in infinite loop. So to prevent that, index is just increased by 1 here. Also, we will be querying 1 less than the current element, because we are required to count the number of smaller elements, not smaller than or equal to. So counting the smaller element corresponds to what is the sum of the elements up to index on this particular array value. So here, instead of getting the sum up to array index I minus 1, I'm querying for array index I, and while updating it, I'm just adding 1 to index 1 at the index array of I plus 1. So basically, instead of writing this minus 1 and this, I have just written like this. So basically, adding 1 to both. So this is just for preventing infinite loop here due to this particular logic. So basically, it is for offsetting the rightmost bit, rightmost set bit. Yeah. So if it is 0, then it can cause infinite loop. I mean, if we make it 0. So yeah. So the sum of all the elements, since we are always adding 1 whenever we are visiting a particular value, the sum of all the numbers up to index array I plus 1 will represent actually the count of elements which are uh, there up to a particular index. So suppose here, suppose this is our array of binary index tree. I mean, actually it is a map of integer integer, but just for the sake of understanding, I mean, we can assume it to be array. So first we encountered 4 instead of, okay, so we are querying for the count of elements up to 4. Okay, so count up to 4 is 0. So basically sum up to this is representing the count. Actually sum from this to this, actually, because here also we are incrementing on the index whatever we are receiving here by 1. So it will be actually returning the sum up to this particular index, I mean 1 to 5. Okay. Now we are updating the next array index at the array of I plus 1 by 1. So we are incrementing by 1 here using this logic. So we are passing value here, and value is always 1 for this particular case. So the count here will become 1. Okay. Now we received 11. So 11, when we receive 11, we will be querying up to 11. So sum up to this 11 is 1. So this was 1. and then we are incrementing the count at index 12. Okay. Similarly, for 0, we will be querying up to 1, basically 1 to 1. This count is actually 0, so we are actually, after getting the count, we are actually incrementing it to 1. So if it is not filled, let's assume it to be 0, because anyways I've written get our default as 0, and here also get our default at index equal to 0. Yeah, so if the value is not there for a particular index, the default value is 0. Similarly, for the 3, uh, we will be querying up to 3, from 1 to 3. The count is 1. So here, this count is 1 actually, and then we will be setting it to 1, like that. So similarly, we will get some and query it like that. Okay, so this line is actually for this line is for setting the rightmost bit, and this is for unsetting the rightmost bit. Okay, so if we want to go in details of binary index tree, so this is actually a summary of how we actually store the values, and how it represents the count of all the elements or sum of all the elements up to a particular index. So you can go and read these articles if you are not comfortable with binary index tree. And yeah, finally, after doing all the processing, we are returning the result. So this is this was the actual result here. So yeah, so this concludes our solution. Please like, share, and subscribe if it is helpful to you. Bye.